Welcome to the Whispering Galaxy, where cosmic mysteries unfold like gentle dreams across the infinite dark. Tonight, we embark on a journey that will take us deep into the heart of stellar furnaces, where the very atoms that make up your body were born in fire and pressure beyond imagination. Before we drift into the cosmic depths together, I'd love to know where you're listening from tonight. Are you tucked away in a cozy corner of Tokyo as midnight approaches? Or perhaps watching from a quiet room in London, while afternoon light filters through your windows? The beauty of our cosmic story is that it connects us all, no matter where we find ourselves on this small blue world, spinning through space. If you enjoy these gentle explorations of the universe, please consider giving this video a like and subscribing to the Whispering Galaxy. Your support helps this little corner of the cosmos grow, and to those already part of our stellar community, thank you. Your presence makes this journey all the more meaningful. Now, settle in comfortably. Let your thoughts slow like distant starlight, because tonight we're going to discover something truly extraordinary. We're going to explore how the twinkling points of light scattered across our night sky are actually cosmic alchemists, transforming the simplest materials into the complex building blocks of worlds and life itself. There's a small chance this story might be too captivating and keep you awake with wonder. But if that happens, at least you'll drift off knowing one of the universe's most beautiful secrets. So let us begin with a question that has whispered through human consciousness since we first gazed upward at the stars. How did those distant points of light manage to create the very substance of everything we know and love? Long before there were planets circling suns, before galaxies painted their spiral arms across the void, the universe was a place of startling simplicity. Imagine a cosmic pantry stocked with only the most basic ingredients. No shelves lined with the rich variety we see today, no complex molecules waiting to be combined into something greater. Instead, there was hydrogen, the lightest and most fundamental of all atoms, filling the vast emptiness like cosmic flour waiting for a baker's touch. Alongside hydrogen drifted helium, slightly more sophisticated, but still wonderfully simple. These two elements dominated everything, making up nearly all the ordinary matter that existed in those early epochs. There was also a whisper of lithium scattered throughout space, but so little that it barely registered against the overwhelming presence of its lighter cousins. This may sound like a disappointing beginning for a universe destined to create such magnificent complexity, but there's profound wisdom in this simplicity. The cosmos began with exactly what it needed, no more and no less. These humble ingredients carried within them the potential for everything that would follow, like seeds that appear ordinary until they find the right soil and conditions to flourish. The hydrogen that filled those early ages was not idle. Each atom consisted of a single proton embraced by a single electron, the most basic arrangement possible in nature's architecture. Yet within this simplicity lay enormous potential energy, waiting for the right conditions to be unlocked. This hydrogen would become the fuel that powers every star, the raw material that gets transformed into all the heavier elements we know today. Helium presented its own quiet elegance. With two protons and typically two neutrons at its heart, it was more stable than hydrogen, but still light enough to drift freely through space. In our modern world, we know helium as the gas that makes balloons float and voices squeaky. But in the early universe, it played a far grander role as one of the essential building blocks from which everything else would emerge. The story of how these elements came to exist takes us back to the very first moments after the Big Bang, when the universe was unimaginably hot and dense. In those initial minutes, conditions were so extreme that atomic nuclei could form through a process we now call Big Bang nucleosynthesis. The universe was like a cosmic forge operating at temperatures and pressures that dwarf anything we can create on Earth. During this brief but crucial period, protons and neutrons collided and stuck together, forming the first atomic nuclei. The process was delicate and required precise timing, The universe had to be hot enough for these particles to overcome their natural tendency to repel each other, but not so hot that the newly formed nuclei would immediately break apart again. First came hydrogen, emerging naturally as single protons captured electrons. Then helium formed as two protons and two neutrons found each other and locked into a stable embrace. Finally, a tiny amount of lithium appeared, created through more complex nuclear reactions that required even more precise conditions. This entire process lasted only about 20 minutes, a cosmic eye blink. But in that brief span, the universe established the foundation for everything that would follow. Roughly 3/4 of all ordinary matter became hydrogen, about 1/4 became helium, and the remaining trace amounts became lithium. Why did the process stop there? Why didn't the early universe continue cooking up carbon, oxygen, iron, and all the other elements we find today? The answer lies in the rapidly changing conditions of the expanding cosmos. As the universe grew larger, it cooled and became less dense. The extreme temperatures and pressures needed to forge heavier elements simply couldn't be maintained in this cooling environment. It's remarkable to consider that for hundreds of millions of years after this initial burst of element creation, the universe remained in what astronomers call the cosmic dark ages. There were no stars to provide light, no galaxies to organize the scattered matter, no planets to offer solid ground, just vast clouds of hydrogen and helium drifting through the darkness, waiting for something to stir them into action. But darkness, as discover, was will preparing for dawn. Within those seemingly empty clouds, gravity was already at work, pulling atoms together ever so slowly. Tiny fluctuations in density, perhaps seeded by quantum effects from the earliest moments of the Big Bang, began to grow. Regions that were slightly denser than their surroundings attracted more matter, becoming denser still. This process continued for millions upon millions of years, with gravity acting as the universe's patient gardener, tending to seeds of matter that would eventually bloom into the first stars. The hydrogen and helium that seemed so limited in variety carried within them the potential for transformation beyond imagination. What's truly beautiful about this early chapter of cosmic history is how it demonstrates that complexity doesn't require complicated beginnings. The universe started with the simplest possible ingredients and yet found a way to create infinite variety. It's a reminder that sometimes the most profound transformations begin with the humblest materials. These primordial elements also teach us about the fundamental interconnectedness of everything we see. The hydrogen that filled the early universe is the same hydrogen that flows in our water and powers our sun. The helium that drifted through cosmic clouds billions of years ago still fills balloons at children's parties and helps deep-sea divers breathe safely at crushing depths. As we continue our journey through the whispering galaxy, we'll discover how gravity gathered these simple ingredients into the first stars, and how those stellar furnaces began a long process of cooking up all the elements that make planets, oceans, and life possible. We'll explore the patient alchemy that transforms hydrogen into carbon, helium into oxygen, and simple atoms into the complex chemistry of existence itself. The universe began as a simple recipe with only 3 main ingredients. But from that humble start, it would learn to create wonders beyond counting. Every atom in your body, every breath you take, every thought that passes through your mind, all of it traces back to those early moments when the cosmos first learned to cook. In our next segment, we'll witness the birth of the first stars and discover how these cosmic furnaces began the greatest transformation in the history of the universe, turning the simple into the sublime through the gentle alchemy of nuclear fire. The transformation from cosmic simplicity to stellar complexity began not with a bang, but with a whisper. Deep within the vast clouds of hydrogen and helium that filled the young universe, gravity worked its quiet magic, drawing atoms together with invisible threads of attraction. These weren't dramatic events that would have caught anyone's attention had anyone been there to watch. Instead, they unfolded over millions of years, as patient and persistent as morning dew gathering on grass. Picture these early clouds not as empty space, but as nurseries waiting to give birth to something magnificent. They were enormous beyond our ability to truly comprehend, stretching across distances that would take light years to cross. Within them, temperatures hovered just a few degrees above absolute zero, so cold that any movement seemed impossible. Yet movement there was, subtle and inexorable, as gravity continued its ancient work. As more and more matter gathered in certain regions, something remarkable began to happen. The center of these growing clumps started to heat up, not from any external fire, but from the simple act of compression. When you squeeze matter together, it warms up, just as a bicycle pump grows hot when you inflate a tire. But in these cosmic clouds, the warming happened on a scale that dwarfs anything we experience on Earth. The process was self-reinforcing, like a gentle spiral leading somewhere wonderful. As the cloud contracted, it heated up. As it heated up, the atoms began to move faster. As they moved faster, collisions became more frequent and more energetic. And as the core grew denser and hotter, gravity's pull became even stronger, drawing in more matter from the surrounding regions. For perhaps 10 million years, this cosmic dance continued. The cloud slowly collapsed inward, its heart growing ever hotter and denser. Temperatures climbed from mere tens of degrees to hundreds, then thousands, then millions of degrees. At these extreme temperatures, something magical happens to matter. Electrons get stripped away from their atomic nuclei, creating a soup of charged particles called plasma. But even this was just preparation for the main event. Deep in the core of this collapsing cloud, where temperatures soared beyond 10 million degrees and pressures reached unimaginable extremes, the fundamental preparing forces of nature were to perform their most spectacular trick. The hydrogen nuclei, normally content to repel each other with their matching positive charges, were being squeezed together with such force that they had nowhere to run. At these incredible conditions, the strong nuclear force finally overpowered the electromagnetic repulsion between protons. When two hydrogen nuclei collided with enough energy, they stuck together, beginning a chain reaction that would change the universe forever. This was the moment of stellar ignition, the birth of nuclear fusion, and the lighting of the first star. The energy released by this initial fusion was beyond description. In an instant, the collapsing cloud found a new source of power pushing outward, counteracting gravity's inward pull. The star achieved what physicists call hydrostatic equilibrium, a delicate balance between the crushing force of gravity and the explosive power of nuclear fusion. It was like a cosmic tug-of-war where neither side could claim victory, creating a stable platform for the universe's greatest cooking show. Inside this new nuclear-born star, hydrogeny were being transformed into helium at rate that boggles the mind. Every second, millions upon millions of fusion reactions took place, each one converting a tiny bit of mass into pure energy according to Einstein's famous equation. The star began to shine, sending its light racing outward through space at speed incredible, announcing to the cosmos that something new and wonderful had been born. But this first generation of stars was different from the ones we see today. They were massive beyond our current experience, some containing hundreds of times more matter than our own sun. They burned with incredible intensity, their surfaces blazing at temperatures that made them shine with brilliant blue-white light. These stellar giants lived fast and died young, consuming their hydrogen fuel at a prodigious rate. Within their cores, temperatures climbed even higher than those required for simple hydrogen fusion. When the hydrogen in the center began to run low, gravity squeezed the core tighter still, raising temperatures to the point where helium itself could fuse. 3 helium nuclei, in a delicate cosmic dance, combined to form carbon in a process so improbable that it seems miraculous. This triple alpha process, as scientists call it, required conditions so precise that it's remarkable it happens at all. Yet happen it did, and with the creation of carbon, the universe crossed a threshold. For the first time since those initial minutes after the Big Bang, new elements were being born. The stellar kitchen was open for business, and it would never close again. These massive first stars didn't stop at carbon. As their cores continued to heat up, they began fusing carbon into oxygen, oxygen into neon, neon into magnesium, and onward up the periodic table. Each step required higher temperatures and greater pressures, pushing the laws of physics to their limits. The stars developed layered structures, like cosmic onions, with different elements being cooked in concentric shells around their cores. The most massive of these ancient giants managed to forge elements all the way up to iron, the most stable nucleus in nature. But iron presented a problem. Unlike all the lighter elements that had come before, fusing iron doesn't release energy, it requires energy. When a star's core filled with iron, its long battle against gravity was finally lost. What happened next was one of the most violent events the universe had ever witnessed. The iron core collapsed in less than a second, crushing matter to densities that rival atomic nuclei. The outer layers of the star, no longer supported by the outward pressure of fusion, crashed inward at speeds approaching that of light itself. When this infalling material struck the incredibly dense core, it rebounded explosively, creating a supernova that could outshine an entire galaxy. These stellar explosions were the universe's first great act of generosity. All the elements that had been carefully cooked in the stellar core over millions of years were suddenly flung into space at enormous speeds. Carbon, oxygen, neon, magnesium, silicon, iron of other elements were scattered across the galaxy, and dozens like seeds on fertile ground. But the supernova did more than just distribute existing elements. In the incredible of the explosion conditions itself, with temperatures and pressures that exceeded even in those stellar cores, elements heavier than iron were forged for the first time. Gold, silver, platinum, uranium, and many others were created in those brief, violent moments and hurled into the cosmic winds. As these first supernovae faded, they left behind expanding shells of enriched gas and dust. The universe was no longer the simple mixture of hydrogen and helium it had been for hundreds of millions of years. Now it contained the something raw materials for far more complex and interesting. The death of each first-generation star seeded vast regions of space with heavy elements. These enriched gases mixed with the remaining hydrogen and helium, creating clouds with a more complex chemistry than had ever existed before. And within these enriched clouds, gravity began its patient work once again, gathering matter into new centers of condensation. The second generation of stars that formed from these enriched clouds were different from their predecessors. They contained small but crucial amounts of carbon, oxygen, and iron mixed in with their hydrogen and helium. This may seem like a minor change, but it had profound consequences for how these stars behaved and what they could create. Heavy elements are incredibly efficient at absorbing and re-emitting radiation. Even tiny amounts of them can dramatically change how energy flows through a star's interior. This allowed the second-generation stars to be more diverse in their sizes and lifetimes. Some were still massive giants that lived brief, brilliant lives. Others were more modest, like our own sun, destined to shine steadily for billions of years. These longer-lived stars became the universe's most patient chefs, slowly and carefully transforming their hydrogen fuel into helium over timescales that span geological ages. Their steady burning created stable environments that would prove crucial for what was to come. Around some of these stars, the enriched dust and gas began to condense into solid grains, then pebbles, then planetesimals, and finally into full-fledged planets. The cosmic recipe was becoming more sophisticated with each passing eon. What had started as a simple mixture of the lightest elements was evolving into a complex interplay of matter and energy, gravity and fusion, creation and destruction. The universe was learning to cook, and its culinary skills were improving with every stellar generation. As we drift deeper into our exploration of the Whispering Galaxy, we'll discover how this ancient alchemy continues today in stars both near and far. We'll explore the delicate processes that create the oxygen we breathe, the carbon that forms our bodies, and the iron that flows through our veins. Every element tells a story of stellar birth and death, of cosmic patience and explosive transformation. The first stars may be long gone, their light having travelled across the universe for billions of years before reaching us, but their legacy lives on in every atom around us. They were the pioneers of complexity, the first to transform the universe from a place of simple beauty into a cosmos capable of infinite wonder. The gentle dance of stellar creation continues today, painting new masterpieces across the cosmic canvas with each passing million years. In observatories perched on mountaintops and satellites drifting silently through space, we can witness this ancient artistry still unfolding, still writing the next chapters of the elemental story that connects us all to the hearts of distant suns. Modern stars come in a breathtaking variety of sizes, colours, and temperaments. Some are red dwarfs, barely massive enough to sustain fusion, glowing with the soft warmth of cosmic embers that will burn for trillions of years. Others are blue giants, massive beyond imagination, consuming their hydrogen fuel with such ferocity that they'll exhaust themselves in mere millions of years. Between these extremes lies our own Sun, a middle-aged star of modest proportions that has been steadily converting hydrogen to helium for nearly 5 billion years. Each type of star contributes its own unique flavors to the cosmic recipe. The smallest red dwarfs are the universe's most conservative cooks, burning their fuel so slowly and efficiently that they'll outlive nearly every other object in the cosmos. They represent stellar longevity at its finest, proof that sometimes the gentlest approach yields the most enduring results. Medium-sized stars like our Sun follow a more complex culinary path. For most of their lives, they contentedly fuse hydrogen in their cores, maintaining the delicate balance between gravitational collapse and nuclear fire. But as their hydrogen supplies dwindle, they begin to evolve, their outer layers swelling into red giants while their cores contract and heat up. This transformation unlocks new fusion reactions, allowing helium to combine into carbon and oxygen in the stellar interior. When these sun-like stars reach the end of their lives, they don't explode in the dramatic fashion of their massive cousins. Instead, they gently puff off their outer layers, creating beautiful planetary nebulae that glow like cosmic flowers in the darkness. These expanding shells of gas carry with them the carbon and oxygen forged in the stellar core, distributing these life-essential elements throughout the galaxy with elegant grace. The most massive stars follow an entirely different recipe, one that leads to the creation of nearly every element heavier than helium. In their cores, temperatures and pressures reach such extremes that they can fuse elements far beyond what smaller stars achieve. Silicon burns into iron, creating the cosmic stopping point where fusion can proceed no further. These stellar giants build up their heavy element cores like cosmic layer cakes, with different fusion reactions occurring at different depths. But it's in the spectacular death throes of these massive stars that the universe's most dramatic cooking takes place. When the iron core can no longer support itself against gravity's relentless pull, collapse happens with shocking suddenness. In less than a second, matter that once filled a space larger than Earth compresses into a sphere barely 20 kilometers across. The resulting explosion sends shock waves racing outward at speeds that approach that of light itself. In those brief moments of supernova violence, conditions become more extreme than anything that exists in normal stellar interiors. Temperatures soar to billions of degrees, and the flood of neutrons becomes so intense that atomic nuclei can capture them faster than they can decay. This rapid neutron capture process creates elements far heavier than iron, forging gold, platinum, uranium, and dozens of other rare elements in the cosmic furnace of stellar death. These supernovae scatter their precious cargo across vast distances, enriching enormous volumes of space with heavy elements. The shock waves they generate also compress nearby clouds of gas and dust, triggering the formation of new stars from material that hastened within the ashes of previous stellar generations. It's a beautiful cycle of death and rebirth that has been operating for billions of years, gradually enriching the galaxy with the ingredients necessary for planets and life. But supernovae aren't the only cosmic events capable of creating heavy elements. In recent years, astronomers have discovered another type of stellar collision that produces its own unique signature in the periodic table. When two neutron stars, those incredibly dense remnants of massive stars, spiral into each other and merge, they create what's called a kilonova. These events are rarer than supernovae, but produce conditions even more extreme, forging elements that are difficult or impossible to create through other processes. The collision of neutron stars creates a brief but incredibly intense burst of neutron radiation. In this environment, atomic nuclei can capture neutrons at such a rapid rate that they build up into some of the heaviest elements in the periodic table. Much of the gold and platinum in our galaxy likely originated in these rare but spectacular cosmic crashes, making every piece of jewelry a memento of one of the universe's most violent events. These discoveries have revolutionized our understanding of where elements come from. Different stellar processes contribute different ingredients to the cosmic recipe, each adding its own special flavors to the galactic mixture. Hydrogen and helium come from the Big Bang itself. Carbon, nitrogen, and oxygen are primarily cooked in the cores of intermediate mass stars. Iron and many other heavy metals are forged in massive stars and distributed by supernova. The very heaviest elements, including much of the gold and platinum we treasure, are created in the collisions of neutron stars and other exotic processes. The beauty of this system lies in its patience and persistence. Stars live for millions, billions, even trillions of years, slowly converting simple elements into more complex ones. When they die, they don't selfishly hoard their creations, but instead scatter them generously throughout space, where they become available for the next generation of stars and planets. It's a cosmic gift economy on grandest possible the scale, where each stellar generation builds upon the contributions of those that came before. This ongoing process of stellar nucleosynthesis is why astronomers often describe the universe as evolving chemically over time. The first galaxies that formed billions of years ago contained almost no heavy elements, making it impossible for Earth-like planets to exist. But with each passing billion years, successive generations of stars have enriched the galactic environment, making it increasingly hospitable to the formation of rocky worlds and the complex chemistry that life requires. Our own solar system formed relatively recently in cosmic terms, about 4.5 billion years ago, from a cloud of gas and dust that had already been enriched by countless previous generations of stars. This is why Earth contains such a rich variety of elements, from the iron in its core, to the oxygen in its atmosphere, to the carbon in every living cell. We are the beneficiaries of billions of years of stellar alchemy, inheritors of a cosmic legacy that stretches back nearly to the beginning of time itself. Even now, as you listen to these words, the process continues. In stellar nurseries like the Orion Nebula, new stars are being born from clouds enriched with the ashes of ancient supernova. In the cores of red giants scattered throughout our galaxy, helium is being fused into carbon and oxygen that will one day enrich future generations of stars. And in the hearts of massive blue stars, silicon is being converted into iron in the final moments before these stellar titans exhaust their fuel. and explode in magnificent displays of cosmic fireworks. The elements being created today in distant stellar furnaces may someday become part of planets orbiting stars not yet born. They may flow through alien rivers, form the bones of creatures we can't forms yet imagine, or support of life so different from our own that we wouldn't recognize them as such. The cosmic recipe is still being written, still adding new ingredients to the universal cookbook with each stellar birth and death. This perspective transforms how we think about our place in the cosmos. We're not separate from the stars, observing them from a safe distance. We are intimately connected to them, made from the very elements they've spent billions of years creating. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the nuclear furnaces of stars that lived and died long before our sun was born. In the next part of our journey through the whispering galaxy, we'll explore how these stellar ingredients came together to form our own world, and how the elements created in distant stars eventually found their way into the chemistry of life itself. We'll discover that the story of the elements is not just a tale of cosmic processes, but the intimate biography of everything we are and everything we'll ever be. As stellar winds carry their precious cargo across the vast emptiness between worlds, we witness one of nature's most patient and profound recycling systems. These elements, forged in the hearts of dying stars, don't simply vanish into the cosmic void. Instead, they begin an odyssey that spans millions of years, drifting through space like seeds scattered by an invisible gardener, waiting for the right conditions to take root and grow into something magnificent. The journey begins when stellar explosions hurl enriched material outward at tremendous speeds. Supernova shockwaves sweep up surrounding gas and dust, creating expanding bubbles of hot, element-rich plasma that can stretch across dozens of light years. These stellar remnants don't travel alone. They mix and mingle with the thin medium that fills the space between stars, gradually cooling and condensing as they drift through the galaxy's spiral arms. Picture these cosmic winds as invisible rivers carrying the treasures of dead stars to distant shores. Carbon atoms that once burned in stellar cores now float freely through space, occasionally bumping into oxygen atoms created in different stars at different times. Iron nuclei, born in the violent collapse of massive suns, drift alongside silicon and magnesium, all of them destined for unknown futures in worlds not yet imagined. The interstellar medium, that vast ocean of space between the stars, becomes increasingly enriched with each passing eon. What was once nearly pure hydrogen and helium gradually transforms into a more complex mixture, seasoned with the ashes of countless stellar generations. This enrichment happens slowly, almost imperceptibly, but with inexorable persistence. Each supernova adds its contribution, each dying star releases its carefully crafted elements, and the galaxy becomes a richer, more diverse place. Gravity never rests in this cosmic dance. Even as stellar winds scatter elements across vast distances, the same force that once gathered hydrogen into the first stars continues its patient work. Dense regions within these enriched clouds begin to contract, just as they did billions of years ago, but now the process unfolds with access to a far more sophisticated palette of ingredients. When these second and third generation clouds collapse to form new stars, something remarkable happens. The presence of even tiny amounts of heavy elements changes everything. These atoms are incredibly efficient at absorbing and re-emitting light, acting like cosmic thermostats that help regulate the temperature and pressure within the forming star. This allows for a much and lifetimes than greater variety of stellar masses was possible in the early universe. Some of the new stars that form are modest, long-lived affairs like our own sun, destined to burn steadily for billions of years. Others are massive, short-lived giants that will quickly exhaust their fuel and explode, adding their own contributions to the galactic mixture. But perhaps most importantly, some of these enriched clouds don't collapse into stars at all. Instead, they form the raw material for something entirely new in cosmic history: planets. The formation of planets requires dust, and dust requires heavy elements. Silicon and oxygen combine to form tiny grains of rock. Iron atoms cluster together into microscopic metallic particles. Carbon creates complex molecules that can serve as the building blocks for even more elaborate chemistry. Without the enrichment provided by previous stellar generations, these solid particles simply couldn't exist. As new solar systems form within these enriched clouds, the dust grains begin to stick together through a process that's both delicate and robust. Electrostatic forces and gentle collisions allow particles to aggregate into larger and larger clumps. Over millions of years, these clumps grow into planetesimals, then into full-sized worlds with their own unique chemical signatures determined by the stellar ashes from which they formed. Our own solar system represents a perfect example of this cosmic inheritance in action. The Sun formed from a cloud that had been enriched by countless previous generations of stars, giving it access to all the elements necessary to create a diverse family of worlds. The rocky inner planets, including Earth, condensed from the heavier elements that could survive the Sun's fierce radiation. The gas giants formed in the cooler outer regions, where lighter compounds could condense into solid grains that served as seeds for massive atmospheric accumulation. Earth's particular chemical composition tells the story of its stellar ancestry with remarkable precision. The iron that dominates our planet's core was forged in massive stars that exploded billions of years before our solar system existed. The silicon and oxygen that make up most of our planet's rocky mantle were created in intermediate mass stars during their red giant phases. Even the water that fills our oceans represents a marriage between hydrogen from the Big Bang and oxygen from stellar fusion, brought together in the cold depths of space before finding its way to our world. But the story doesn't end with planetary formation. Once worlds like Earth had assembled themselves from stellar debris, they became laboratories for an entirely new kind of chemistry. The elements that had been created separately in different stars and scattered across the galaxy were now concentrated in one place, able to interact in ways that had never been possible in the harsh environment of interstellar space. Liquid water, made possible by the presence of heavy elements in our planet's atmosphere and interior, became the medium for chemical reactions of unprecedented complexity. Carbon, that versatile architect of molecular structures, found itself in an environment where it could form the long chains and complex arrangements that serve as the foundation for biology. Phosphorus, forged in the death throes of massive stars, became available to store and transfer energy in living systems. The emergence of life on Earth represents perhaps the most remarkable chapter in the story of stellar recycling. Every atom in every living cell can trace its origin back to nuclear fusion in stellar cores, or to the primordial nucleosynthesis that followed the Big Bang. The carbon that forms the backbone of DNA, the oxygen that powers cellular respiration, the calcium that strengthens bones and shells, the iron that carries oxygen through bloodstreams. All of these life-essential elements were gifts from stars that lived and died long before Earth was even a glimmer in the cosmic eye. This perspective transforms our understanding of life from something separate and special into something that's deeply integrated with the broader cosmic story. We're not observers watching the universe from the outside. We are the universe becoming aware of itself, stellar matter organized in such a way that it can contemplate its own origins and wonder at its own complexity. The elements that flow through our bodies today have been on journeys that span billions of years and countless light years of space. The calcium in your bones may have drifted through interstellar space for eons before becoming part of the cloud that formed our solar system. The iron in your blood was forged in the core of a massive star that exploded in a supernova so brilliant it may have outshone an entire galaxy. The oxygen you're breathing right now was created when helium nuclei fused together in the heart of a red giant star somewhere in the ancient Milky Way. This cosmic recycling continues today on scales both vast and intimate. Every breath you take releases carbon dioxide into the atmosphere, where it may be absorbed by plants and incorporated into their tissues, or it may drift into the upper atmosphere and eventually escape into space, beginning another long journey through the galaxy. The elements in your body are borrowed, not owned, part of a cosmic circulation system that has been operating for billions of years and will continue long after our sun has exhausted its fuel and our planet has returned to dust. Modern astronomy allows us to witness this recycling process in action across the galaxy. We can observe stellar nurseries where new stars are being born from clouds enriched with the ashes of previous stellar generations. We can watch planetary nebulae expanding outward from dying stars, carrying freshly forged carbon and oxygen into the interstellar medium. We can detect the signatures of ancient supernova in the chemical composition of stars forming today, reading the history of stellar death and renewal written in the language of spectroscopy. The Hubble Space Telescope and other observatories have revealed that this process of cosmic recycling operates on truly galactic scales. Supernova explosions can trigger the formation of new stars hundreds of light years away from the original explosion. The shockwaves from massive stellar deaths compress nearby clouds of gas and dust, causing them to collapse and ignite their own nuclear fires. It's a chain reaction of creation and destruction that has been shaping the structure and evolution of our galaxy for over 10 billion years. Even more remarkably, we now know that this recycling operates between galaxies as well as within them. Powerful stellar winds and supernova explosions can actually blow enriched material completely out of smaller galaxies, carrying heavy elements into the vast spaces between galactic systems. These intergalactic winds can travel for millions of years before being captured by the gravitational field of another galaxy, where they contribute to new episodes of star and planet formation. This cosmic perspective reveals that the story of the elements is also the story of connectivity and relationship on the grandest possible scale. Nothing in the universe exists in isolation. Every atom, every molecule, every grain of dust is part of a vast web of exchange and transformation that connects the smallest scales of matter to the larger structures in the cosmos. The elements created in stellar cores don't simply accumulate over time. They participate in cycles of concentration and dispersal, gathering into stars and planets, then being scattered once again by stellar winds and gravitational interactions. It's a cosmic metabolism that keeps the universe dynamic and alive, preventing it from settling into static equilibrium and ensuring that new forms to emerge of complexity can continue. As we continue our gentle drift through the whispering galaxy, we'll discover how this ancient process of stellar alchemy continues to shape our world today, and how the elements forged in distant suns have become the very substance of our thoughts, dreams, and capacity for wonder. The cosmic kitchen remains open, still cooking new batches of elements with each stellar generation, still writing new chapters in the greatest recipe book ever conceived. The profound truth that emerges from this cosmic perspective is both humbling and deeply comforting. You are not merely a collection of atoms that happen to find themselves together by chance. You are the culmination of billions of years of stellar craftsmanship, a living library containing the history of the universe itself. Every element that flows through your body carries with it a story that stretches back to the very heart of ancient suns. Consider the oxygen that fills your lungs with each breath you take. This isn't just any oxygen, pulled from some cosmic storehouse of spare parts. These particular atoms were born in the nuclear furnace of a star that may have been dozens of times more massive than our sun. For millions of years, that ancient giant fused helium nuclei together in its blazing core, creating oxygen through processes so energetic they dwarf anything we can imagine. When that star finally exhausted its fuel and exploded in a supernova that briefly outshone an entire galaxy, your oxygen atoms were hurled across space at speeds that boggle the mind. For eons beyond counting, those oxygen atoms drifted through the cold emptiness between stars, perhaps becoming part of vast molecular clouds that glowed faintly in the darkness. They may have witnessed the birth of other stars, felt the gravitational pull of passing worlds, or danced in the shock waves of distant explosions. Eventually, they found their way into the cloud of gas and dust that would collapse to form our solar system, becoming part of Earth's atmosphere through processes we're only beginning to understand. Now, as you breathe, those same atoms flow into your bloodstream and travel to every cell in your body, where they participate in the chemical reactions that keep you alive. The oxygen that once burned in the heart of a star now burns in your cells, releasing the energy you need to think, to move, to wonder about your place in this vast cosmos. It's a connection so direct and intimate that it takes your breath away, which is perhaps fitting for atoms that have travelled so far to reach your lungs. The carbon that forms the backbone of every organic molecule in your body tells an equally remarkable story. Carbon is one of the most challenging elements for stars to create, requiring a process so improbable that it seems almost miraculous. Deep within stellar cores, 3 helium nuclei must collide almost simultaneously, overcoming enormous odds to stick together and form a carbon nucleus. This triple collision happens in a fleeting moment when conditions are just right, like catching lightning in a bottle on a cosmic scale. Yet somehow, against all probability, it happens billions of times over in every star massive enough to reach the required temperatures. The carbon atoms that now form your DNA, your proteins, and the sugars that fuel your thoughts were each born in such a moment of stellar precision. They represent victories against entropy, triumphs of order over chaos, written in the language of nuclear physics and delivered across space and time to become part of your story. The iron that courses through your veins in every heartbeat carries perhaps the most dramatic tale of all. Iron can only be created in the final moments of a massive star's life, when temperatures in the core reach billions of degrees and the star teeters on the edge of catastrophic collapse. Unlike lighter elements, iron cannot provide energy when it fuses with other nuclei. Instead, it acts like stellar poison, accumulating in the core until the star can no longer support its own weight. When that inevitable moment arrives, the collapse happens with shocking suddenness. In less than a second, matter that once occupied a volume larger than Earth compresses into a sphere barely 20 kilometers across. The resulting explosion sends shockwaves racing outward at nearly the speed of light, tearing the star apart and flinging its iron-rich core across the galaxy. The iron atoms now carrying oxygen through your bloodstream were forged in such violence, baptized by fire, and scattered by cosmic forces beyond imagination. Every beat of your heart is powered by these stellar remnants, each pulse a quiet tribute to stars that died billions of years ago. The hemoglobin molecules that carry oxygen through your body are built around iron atoms that once resided in stellar cores, hotter than anything we could ever create on Earth. Your very ability to breathe, to live, to contemplate these mysteries depends on the generosity of long-dead suns that scattered their treasures across the void. Even the calcium that gives strength to your bones and teeth has its own stellar biography. Calcium forms in the silicon-burning shells of massive stars during their final evolutionary phases, when these stellar giants have become layered like cosmic onions with different fusion reactions occurring at different depths. The calcium atoms now providing structure to your skeleton were once part of these stellar furnaces, created in temperatures exceeding 1 billion degrees, and pressures that compress matter beyond anything we can replicate in our laboratories. The phosphorus that stores energy in your cells and forms the backbone of your genetic code has an even more exotic origin. This essential element can only be created in significant quantities during the explosive final moments of certain types of stellar evolution, when shockwaves and nuclei. Without these relatively rare atomic extreme temperatures combined to forge phosphorus, life as we know it would be impossible. Yet it represents less than 1% of your body's mass. You are built from stellar abundance and stellar scarcity in equal measure. What makes this cosmic inheritance even more remarkable is how perfectly suited these stellar products are for the chemistry of life. Carbon's ability to form long chains and complex structures, oxygen's eagerness to participate in energy-releasing reactions, iron's talent for reversibly binding to other molecules, calcium's tendency to form strong but flexible structures. All of these properties that make life possible are simply consequences of how these atoms were forged in stellar cores billions of years ago. It's as if the universe spent eons learning how to cook the perfect recipe for complexity, with each generation of stars adding new ingredients and the elements that flow through your body refining the mixture aren't random selections from a cosmic grab bag. They're the carefully crafted products of stellar evolution, tested and refined over billions of years of cosmic history. This stellar heritage extends beyond the major elements that dominate your body's composition. The trace amounts of zinc that help your enzymes function. The tiny quantities of iodine that regulate your metabolism. The microscopic amounts of copper that assist in oxygen transport. All of these elements have their own stellar stories. Some were created in the cores of intermediate mass stars during their red giant phases. Others were forged in the neutron-rich environments of supernova explosions. Still others may have been born in the collision of neutron stars, events so rare and violent that they occur only once every few 100,000 years in a typical galaxy. Yet here they all are, gathered together in the chemistry of your body, each playing its own small but crucial role in keeping you alive and aware. You are not just made of stardust in some poetic, metaphorical sense. You are literally composed of atoms that were manufactured in stellar factories, quality tested in the crucible of nuclear fusion, and delivered to Earth through the patient work of cosmic recycling systems that operate on timescales beyond human comprehension. This perspective transforms our understanding of human consciousness itself. Your thoughts, your memories, your capacity to feel wonder and ask questions about the universe, all of these emerge from the intricate dance of atoms that were born in stellar cores. The neural networks that generate your consciousness are built from carbon, oxygen, nitrogen, and phosphorus that traveled across space and time to be here now, participating in the universe's ongoing effort to understand itself. When you look up at the night sky and feel a sense of connection to the stars, you're experiencing something profound and literally true. Those distant points of light are not alien and separate from you. They are your ancestors in the most fundamental sense possible, the cosmic forges that created the very atoms from which you are constructed. The light that reaches your eyes from distant stars is a family reunion of sorts, photons greeting the stellar matter that has become organized into the complex structure of your visual system. This cosmic kinship extends to every living thing on Earth. The oak tree outside your window, the birds that nest in its branches, the microbes in the soil beneath its roots, all are built from the same stellar inheritance. We share not just a common ancestry with all life on Earth, but a deeper connection that reaches back to the hearts of ancient suns. Every atom of carbon in every living cell, every molecule of oxygen in every breath, every trace of iron in every drop of blood, all were gifts from stars that lived and died long before our world was born. The elements continue their cosmic journey even now. The atoms that currently make up your body are only temporary visitors, borrowed from the vast circulation system that moves matter between stars, planets, and living things. The carbon you exhale with each breath may one day be incorporated into a plant, or drift into the upper atmosphere and eventually escape into space, beginning another journey that could last millions of years. The calcium in your bones will one day return to the soil, perhaps to be taken up by future trees, or washed into the sea, where it might become part of a shell or coral reef. In this way, you participate in the ongoing cycle of cosmic recycling that has been operating since the first stars began to shine. You are not just a product of stellar evolution, but an active participant in it, a temporary organization of stellar matter that has achieved the remarkable ability to contemplate its own origins and wonder at the beauty of the universe that created it. As we near the gentle conclusion of our journey through the whispering galaxy, we find ourselves not at an ending, but at a moment of quiet recognition. The story of how stars forge the elements is not just a tale of distant cosmic processes, but the most intimate biography possible. It is your story, written in the language of nuclear physics and told through the patient alchemy of stellar fire. Every atom in your body is a word in this cosmic narrative. Every breath a sentence in an epic that spans billions of years and countless light years of space. And so, dear wanderers of the cosmos, our gentle journey through the stellar forges comes to its quiet close. We have travelled together from the universe's humble beginnings with only hydrogen and helium, witnessed the birth of the first stars, and followed the ancient alchemy that transforms simple atoms into the complex chemistry of existence itself. Every element that flows through your body, every breath you take, every heartbeat powered by stellar iron, connects you intimately to the hearts of distant suns. You are not merely observing the universe from afar, you are the universe contemplating itself through eyes made of starlight. Thank you for drifting with me through these cosmic mysteries tonight. Until we meet again beneath the whispering stars, may you carry with you the beautiful truth that you are, quite literally, made of wonder